Okay, um, so we have covered switch mode inverter. We have covered the two types of inverter, whereby it depends on the output of the inverter, whether it's a single phase or three-phase inverter. We have looked into the types of single phase inverter, depending on the whether it's a half bridge or full bridge circuit, and but those two circuits can be controlled by three techniques, which are the square wave technique, the quasi square wave, and the sinusoidal PWM. All right. So today, the PWM waveforms, which is the control signals to the switches, can be realized or can be obtained conventionally by comparing two signal generator, which is the sinusoidal modulating signals, and then we're going to compare with the triangular carrier signals, two generator, right? And then there is a comparator that compare those two, and then whenever the modulating signals is greater than the triangular carrier signals, there will be a pass uh, to the switch. So there is a convention way to generate the PWM waveform. So I'm not going to browse to the PWM section. Just before that, okay, so we look into this part whereby there are two techniques, which is a unipolar, two types of PWM, unipolar and bipolar PWM. Unipolar, the triangular signals consist only the positive value, but bipolar we have two. It consists of positive and negative triangular carrier signals. So this is a unipolar PWM, right? And then we have this bipolar PWM, positive and negative value. So conventionally, as is in this circuit, what we do is to generate all these pulses. We have two signal generator, the sinusoidal slow frequency generator, and then we have this high frequency triangular carry signals, and then we compare, and then we have this comparator. So whenever VM, the modulating signal, is greater than the triangular carrier signals, it will produce a pass of 1, and then it will pass 0, otherwise it's going to be pass 0. So um, that is a conventional way to do that. And by varying the modulation index, which is the amplitude of the modulating signals, we can vary the width of the pass, isn't it? Right. So today, now we're going to look into the how this pulse can be obtained. All these pulse can be obtained by using microprocessor, in which we need, depending on the frequency of the carrier signals, depending on the modulation index, the the pulse here, or the angles for each pulse, is varied, isn't it? It will be varied depending on the modulating signal, modulation index, as well as the carrier frequency. So in order for us to generate the pulse by using the microprocessor, we need to identify what is these angles. Each of these pulse, what will be the angles for that? Is there any equation that can describe this? So once we have that general equations to describe all these pulses, then you can easily tell the microprocessor to generate the pulse at certain angles. Right. Okay, so the idea is, when you want to look at the details uh, of the analysis of this PWM, the basic thing is we need to establish a equation that define the positive slope of these triangular carrier signals and negative slope line for the triangular carrier signals. Because we know whenever it intersects, there is an intersection between these two lines with the modulating signals, it will produce the pulse, isn't it? It will produce at each intersection. So as once we know the equation for both straight line here, we just simply equate these two lines with the modulus, the sinusoidal signals equation, and therefore you can determine what is these angles. Okay, right. So now we look into, that's the idea, and now we look into the detail of the analysis. Okay, so this is the detail, the notes for the detailed analysis of PWM. Right, so we start with the unipolar PWM first. Unipolar PWM, therefore your triangular carrier signals only consists the positive part. So we have a 0 and 1. And please take note that we assume that these triangular carrier signals is the W shape, because it start with 1. It is W shaped type of triangular carrier signals. Okay, so we can also have M type, whereby it start with 0, isn't it? Right, so you can also have this type of PWM. Therefore you will be a different equation, that the linear the line equation for each line there for the M shape PWM. So never mind, we start with a unipolar SPWM, and we assume this is W shape first. Right, so it's just simply equation of the general straight line equation, whereby you have y equals to mx plus c, isn't it? Mx plus c, that's it. We need to get what is the m, the slope, sorry, and what is the c, right? The intersection to the with the y axis. Okay, so the other thing is we need to determine first, this is the period for the triangular carrier signals. Okay, this is the period for the carrier signals. Okay, so we need to know that this is the carrier frequency, right? Carrier frequency, and TC is the period for each of the carrier signals here. Right? So here, since we do the W shape carrier signals, so the TC will be from that tip to another tip, right? So this is the period for one cycle of the carrier signals. And then we normalize, we do the normalize of the amplitude, so that we have VM, VC, VC peak, the carrier signals, the peak amplitude of the carrier signals equals to 1. And therefore, if I can extend that so that you get the modulating signal, so these modulating signals VM peak equals to for example 0.8, isn't it? 0.8, 0.6. So we know that the modulation index okay, the modulation index equals to VM peak divided by VC peak. Okay, the peak of the two value. Right, so so that is the TC, the period for the carrier signals. And then we need to define correctly the number of the order number of this slope, or sorry, of this triangular carrier line. Okay, so this will be the first line, isn't it? And that will be the second line, and then sorry, first line for the positive slope. So this is a positive slope, and you have this is a negative slope of the line, and therefore this line is actually the first positive slope line, and that will be the first negative slope line. So this is very important, right? Because all this number will be used to calculate the angles. Because if you mistakenly put the numbers, you instead of you calculate that, you want to determine that angles, instead you give you these the other angles, the other angles, which is a different order of the line numbers. Okay, so that's why here we have this negative slope, isn't it? This is a negative slope, sorry, this is a negative slope, so therefore the first angles or time, this is in terms of time domain, so we have the first negative time will be that intersection between that line, and then the first positive slope will be that, okay, the first positive slope, and then this will be the second negative slope, the second positive slope. Okay, so once you define that, then we look into the detail of the equation. So we start with the first negative slope, which we refer to that line, right? Okay, we refer to that line. So from y equals to mx plus c, m is always what? M, the slope is always delta y divided by delta x, isn't it? Okay, so we have this point as 0, 1, and this point is what we call it, half, isn't it? TC or TC over 2, isn't it? This is TC over 2, so TC over 2, Allah, sorry. So that line will be TC over 2 and 0, xy, and the coordinate xy, and that will be 0, 1, isn't it? So therefore, we will look at the slope, that will be delta y delta x, and therefore that's why you have this minus 1 divided by TC over 2, isn't it? So this is delta y and this is delta x. It's a negative, isn't it? It's a negative because you have a 1 minus 0, and you have 0 minus TC over 2, so that's why you have a negative here. So therefore the equation, the slope for m equals to minus 2 over TC. Okay, and then we know that at this point we have y equals to y0, x equals to TC over 2, and therefore from that information we substitute into that, and therefore we can identify c equals to 1. Of course, obviously we see that this the cross intersection between the line to the y-axis will be at 1, so c equals to 1. Okay, so therefore the equation for the first negative slope equation will be y equals to minus 2 over tcx plus 1, and in time domain we have this equation y and 1 t equals to minus 2 over tct plus 1. So this is time domain. Right, so next we look into the first positive slope, which is we refer to that particular line. Okay, for that first positive slope, and the analysis is very much simple, similar. Now you have m equals to positive 2 over tc, so it's a positive slope, right? So you have 2 over tc, and the rest you can see it's across the intersection with y at minus 1. So it is quite obvious, if we can extend this line, it will cross at minus 1. Okay? So therefore we have c equals to minus 1, and therefore your general equation, the equation for that line, first positive slope line will be y equals to 2 over tcx minus 1, and in terms of domain you have this, right, yp1, so that is actually the first positive slope equation, equals to equals to 2 over tc minus 1, right? So we have two equations there, and then we proceed further and we look into first negative slope, second negative slope, and second positive slope, which refer to that line, second negative slope and second positive slope. So by referring to that two lines there, we have another equation which we found by that equation and that equation. Okay, I leave it to you to do the derivation. We have these two equations, and finally we can actually generalize. Okay, we can generalize the equations by using these two equations: y and k plus 1 t equals to minus 2 over tc. So this is for the negative slope equation. Okay, and this is for positive slope equation, right? So if you want to have the first positive slope, I can zoom that. Okay, if you want to have a first negative slope, so k should be equals to 0, isn't it? Therefore you have y and 1, and then you proceed equals to minus 2 over tc, t plus k equals to 0, therefore equals to plus 1. And if you want to have a second positive slope, yp2 for example, yp2, so k should be equals to 1, isn't it? So if you replace that, you get yp2 because k equals to 1, t equals to 2 over tc minus t minus 2 multiplied by 1, 2 plus minus 3, isn't it? So you have the second positive slope equation, which is equals to that. So we can have, now we have two general equations here to describe all the lines for the triangular carrier signals for unipolar PWM. So this is only true for unipolar PWM, right? Unipolar PWM, and with the W shape, right? W shape form. If you have a M shape, there will be a different equation. You can try that. Okay, please try it yourself. You will get the different general equation for M shape, right? Okay, so once you get the idea, now we need we know that the modulating signals, right? Modulating signal is always sinusoidal waveforms, right? And the equation for that will always be y equals to the peak value Vm peak, then you have sine omega t, isn't it? Yeah? Sine omega t. And because we already said the triangular carrier signals, we already said is a W shape, isn't it? So we already set the triangular signals at 1. We normalize it, so that equals to 1. Okay, so the modulation index MA equals to, you know, it's a Vm peak divided by Vc peak, and that become what? Vm peak divided by 1. Okay, so we have Vm peak equals to the modulation index, right? So therefore your equation now become y ma sine omega t, isn't it? Okay, your modulating signals equation, y equals to ma, see, and therefore if you want to get the intersection between these two lines, we need to equate that, and therefore this we have these two equations. So this is from the sinusoidal signals, modulating signals, ma sine omega t. So t with respect to whatever the general equation for the negative slope. Okay, and then we have minus 2 over tc, t and k plus 1. So this is for the negative slope equation, right? 2k plus 1. So you equate both equations, and therefore you find out that t can be calculated by using this general equation. T and k plus 1 equals to 2k plus 1 minus ma sine omega t and k plus 1 multiplied by tc over 2. So here, be careful. This omega is actually referred to the 2 pi f of the modulating signals. This is not fc. Okay, this is the modulating signal, the 50 hertz frequency, the slow modulating signals here. So 2 pi f is, this is not fc, this is not fc, it's not fc. Okay, fc is actually for that tc, whereby tc equals 1 over fc. Take note of that. Okay, 1 over fc. Right. So and we have another variable, I mean the level, which is the frequency ratio equals to fc divided by f or fm. The modulating signals fm or f, right? So whatever levels that you use. So it is, you understand, this is the triangular carrier frequency divided by the modulating frequency, right? fc over. So that determine fr, and normally fc is very high, let's say 1000 for example, and f equals to 50, so therefore you can have that. So what, 5 with 20, great. So fr equals to 20. So that is a frequency ratio. They are the important terms that you need to remember. Okay, so this is the equation for the negative slope equation, and then this is for the positive slope equation. So we have two. This is a negative slope, and this is for the positive slope. And remember, as what we did for to find the beta, isn't it, in the control rectifier, how to get that beta by using the calculator, isn't it? So you need to use a shift solve everything. There is a note at the end of this note, how to get that value there. Okay, so we're going to look at examples on that later on. Okay, so now you can determine each of these angles or the time, okay, or equivalent to the time by using these two equations. Right, so this is the unipolar. So now we move to bipolar PWM. So for bipolar PWM, remember we have positive and negative values of the triangular carrier signal. So in this case, we start with always we start with 0 there. Okay, we assume we start from 0 there, so we have that triangular carrier signals. Then we extend to the negative a bit, so we start from that to there. Then we have that and the rest. Okay, so therefore this is the level from this point to that point, right? To be consistent with the explanation, so we have this TC described from that point to that point. So this is the period for the carrier frequency. Okay, and then similarly we have this as a first what, positive slope, isn't it? And that will be first negative slope, second positive slope, second negative slope. Right, so we analyze the first positive slope first. First positive slope, so we have this equation y equals to mx plus c. So please refer, just like we did for the unipolar PWM, we get the m, and then c equals to 0 because it's crossed 0 there, right? So we have this equation yp1 4 over tc over t. And then we proceed with the first negative slope, and then finally you have y and 1 equals to 4 c. And we proceed with the second positive slope, second negative slope. I'm not going to go through this, so you just refer back to the notes and try to look at how it is derived. Make sure that you understand and you can redefine or derive from the blank sheet, and then you start to derive. Please do that. Just practice, so that's because sometimes you will be asked to show the derivation to get this, to prove the switching angles. I mean the equation, the general equation for positive negative slope. So you have to do that. Do not just memorize everything. So you need to start from the blank paper and then just start to derive. Okay, so you proceed for a second positive slope, and then we have a third positive slope, and we have these two general equations here. So of course it's different with unipolar PWM. So for positive slope equation, ypk plus 1t 4 over tct minus 4k, and then we have ynk plus 1t minus 4 over tct for the negative slope equation, right? And then therefore you equate again, very similar to previously. We have the same modulating signals here. Okay, same modulating signals. We equate and we have these two general equation to describe for the switching. Now it's a time domain, isn't it? This is in time, but if you multiply by omega, you get the angles. Okay, if you multiply by that angles, we're going to look at the examples of that. If you multiply both equations with omega, so you can have this as the switching angles in radian, omega t, right? So you have and again, this is 2 pi f, the modulating signals, the slow frequency, not the carriers frequency. So omega t. So if you multiply both sides with omega, then you obtain the switching angles. But here we derive for the time, in time domain. Right? So we have two equations again, and therefore from these two equations we can calculate the angles. Right. So we look into the examples. So let's look at this example. Okay. An IGBT inverter circuit employs a switching technique to control its 50 Hz voltage output. The technique utilizes two control signals as shown over one full cycle, full cycles. T1 is the period of the triangular signals, whilst T is the period of the sinusoidal signals. Okay, so very much T1 here is similar to TC in our derivation, and T here is a T, the period for the modulating signals. The amplitudes of the signals are given in per unit basis. So it's the per unit, of course, it's 1, right? It's normalized to per unit basis. So it's 1. And then the modulating signals now have a 0.86. So definitely we know that the modulation index MA equals to 0.86 divided by 1. Is it? Yeah, it's a 0.86. Okay, so the required switching angles for the inverter switch are produced when the two signals intersect. Yes, we're going to find what is the intersection here at each intersection here. So we're going to calculate what are these angles. What are these angles? What are these angles? Okay, by using appropriate terms, describe the principle of the switching technique. So you need to describe. So first is what you can tell, this is bipolar PWM, isn't it? Bipolar PWM. And then what else? The modulation index is 0.86. What else? The frequency. We can determine the frequency, isn't it? Because when we look at the triangular carrier signals, it repeat how many times? 1, 2, 3, 4, 5, 6, and 7. So we know that the FC is 7 times faster than the F, or F1 here, sorry. So for F1 faster than the modulating signals by 7 times. So the frequency ratio is equals to what? F1 over F, or equals to 7. Is it? Okay? The frequency ratio equals to 7. So this is a thing that you need to mention. By using appropriate terms, describe the principle of the switching technique. So first, you list down the all these parameters: the frequency ratio, the modulation index, and bipolar, and then you can describe in terms of how this is produced, isn't it? So you compare, you say that it's modulating signals compared with the triangular carrier signals. Then whenever Vm greater than Vc, you will produce a pulse of 1. Whenever Vm lower than Vc, you will produce a 0. 0, 1, 1, 0, 1, 0, 0. Okay. Number 2, calculate the switching angles for the first half cycle. So this is one full cycle. First half, will be up to that point, instead of 180 degrees. So we need to find all this intersection. What is that? What is that? And then the rest. So how many angles? We know this is 0. The first angle is at 0. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, plus 8. This is 0 again. Very much about 6. 1, 2, 3, 4, 5, 6 angles that you need to calculate. Okay, so we start with the, of course, the first angles here. This is will be the first positive slope, and this is first negative slope. Is it? So we write an equation. I'm going to write here the general equation. We I think go to the next slide. Right. Okay, so we list down this. Okay, and this is the equation for this is the equation for, let me see, TC over 4 m sine plus 4k. Go back to the notes just now. Bipolar, is it? Is it? Okay. M 4k plus MA, so that positive slope. All right, and this is negative slope. So this is equation for positive slope. This is negative slope. Positive slope. This is negative slope. Right. So for the first positive slope, we know that k equals to, of course, k need to be 0, right? So that we have I equal in the equation, this is k plus 1, is it? K is plus I, is it? T and TP k plus 1. In here, just directly put I. So just ignore that. Okay, we can write the equation again, so that we have T P k plus 1 equals to TC over 4. Then we have the general equation M sine omega t, omega t, we do that t what, TP k plus 1. Okay, and then plus 4k, the first slope. TC over 4 m sine omega t plus 4k multiplied by TC over 4. And then for the Tn, k plus 1 equals to TC over 4. Then you have 2 plus 4k minus m sine omega Tn k plus 1. Right? K plus 1. So we start with the first positive slope. Where is it? So first positive slope is that question. So you don't need to do the analysis. We know that exactly this is at 0. So that's why in this solution, it shows that it is 0. Okay? In this case, t equals to 0. And therefore, the first angle will be omega t naught equals to 0 radian. Always put in radian. Okay? Okay. So what about the second second slope? First negative slope. So can I write again? Can I move that per second? So I need to refer to this when I write. Okay, I'm going to go back to that page. Right. For the, so we already saw for first positive slope. Okay, we have done that. We know that k equals to 0 at this point, and we know that t p1 equals to 0, or in terms of angles, omega tp1 equals to 0, and this is actually theta p1 equals to 0. right? So we have analyzed that, and then we proceed with the first negative slope equation. Okay, let's continue. Okay, we have found what will be the first angles here, right? For the first angle, for the first positive slope, we have theta p1 exactly. Obviously, it is a 0 radian, isn't it? So now we're going to look into the first negative slope equation or line, and then we're going to find the second angles here, which is theta n1, isn't it? Yeah, the first negative slope line, and this will be known as theta n1. Okay, for that I use this Jamboard, right? So this is the general equation for both positive and negative slopes, and then we have solved for first positive slope. It is obviously it is at 0 radian. So now we're going to continue with the first negative slope, and therefore k should be equals to 0, 0, and therefore you could obtain t and 1, and you have 2 k equals to 0, then that will be 2 minus ma sine omega t and 1, and you have tc over 4, right? And we know that from the examples here, the molecular index ma equals to 0.86, right? This is 0.86, and then we have this the frequency ratio will be 7 times 7. So we have 1 2 3 4 7. So the carrier frequency is 7 times faster than the modulating signals, and therefore your fr equals to 7. And then 50 hertz, that's the information. Now we try to continue with this, and we know that tc is equals to fc 1 over fc, and omega here is 2 pi f, the modulating signal. Okay, and we know the frequency ratio, which is fc over f equals to 7, and modulating signals ma equals to 0.86. Okay, so we replace this, and it is convenient to convert that into radian. To convert to radian, so what we do is we multiply both sides with omega. Okay, so now we have omega t and 1 equals to 2 minus ma sine, oh, I should have replaced that straight away with 0.86. Then we have sine omega t and 1. This is the original from this, so we have omega t and 1, and we multiply as well omega tc over 4. Okay, so both sides are multiplied with omega, and therefore we have, and now we change that theta and 1 radian per second, radian, and we have 2 minus 0.86 sine, this is theta and 1 again, and then we have omega is 2 pi f divided by 4, and then you have 1 over fc, and we know that f over fc equals to 1 over 7, isn't it, from here? It's a reciprocal, so we have 1 over 7 here. Okay, so we multiply, therefore what left is only 2 divided by that, so 2, so once we have pi over 14, 7 multiplied by 2 is 14. Okay, right, so from there we need to use the calculator fx570 to solve for theta and 1. This is very similar to what we did for finding the beta, isn't it, for the control rectifier. Okay, so here in the lecture notes, if you go the last page here shows you how to do that. So we have assumed 0.86. This is exactly from the examples. And we want to calculate the switching angle at second positive. If we assume this is a second positive, the k equals to 1, then we have TP2 that multiply both sides of the equation with omega to convert into radian. Then this, then finally you have this equation. This is for P2, the second positive slope. So you get theta P2 equals to 4 plus 0.86 sine P2 pi over 14. And then it shows you how to get the angle by using the calculator. So you have to change to radian and rearrange and how to use that. Okay, so I'll leave this for you. Right, and look at the examples again. So by doing that, we're going to just ignore this solution. Just ignore this solution. Just follow what I did and just now. In here, I will share with you this. Okay, so redo it. And then you get the first negative slope is at 21.65. Okay, 21.65. Okay, therefore second angle is 21.65. Next is when k equals to 1, therefore we look into the second angles, the theta p2, isn't it? So this is we jump to theta p2, and therefore you obtain 61.12, or in radian is 1.067. And next you proceed with the second negative slope. Okay, and that will give you 66.96, or equivalently is 1.169 radian. And finally, when we refer back to this equation, this waveforms, now try to identify. We have 0 here. Okay, and then that is equals to 21.65. Okay, this is 21.65, and then here is 61, and this is 66. Okay, this is 66. Go to 66 degrees of things. Okay, now for you to calculate the rest of the angles, when you look at the waveform again, this is a symmetry respect to that axis. Okay, so if we draw a line to 90 degree, right, this is a 90 degree out of 360 degree there. If you look at the peak of these sinusoidal modulating signals, so we see that the rest of the waveform for the first half cycle is actually symmetry to the first 4 angles here, isn't it? So that equals to, that will be equals to that. This will be some of that, symmetry of that, and this is symmetry of that waveform, isn't it? So in order for you to obtain the rest of the angles, yes, you can repeat the calculations for the consequence n, okay, n1, n3, n5, n4. Or what you do is you just simply 180 degree minus this to get that angle. Okay, 180 degree minus 66 something, you get this angle. And then 180 degree minus 61 degree will give you that angles. And then 180 degree minus 21.65 will give you that angles. Okay, so you can only do this if the waveform is symmetry. Symmetry. Okay, so that's why in the solution it only calculate for the first 4 angles, and then for the rest you just simply do this 180 degree minus the angle 66 under that. So now you get all the angles. Okay, right. Next is the question asks you calculate the fundamental component of the DC supply voltage is 400 when the DC supply is 400 volt. So you need to calculate the fundamental component. So what is a fundamental component? Again, when the question asks you about the talk about the fundamental component, that actually refer to the harmonic spectrum. Okay, so when you look into the harmonic spectrum of the PWM waveform, you will get. So before that, we need to look into the PWM signals as well as the output voltage. Okay, so this is only the original modulating and triangular carrier signals. So we need to observe the output voltage, then we can appreciate what is a fundamental. Going to look into that. So now I'm going to simulate first. Let me simulate this bipolar PWM. These examples. Okay, T20 bipolar. So get that. Double click. Okay, so it's a full bridge. Okay, and then you have 0.86. So this is the modulating signal amplitude 0.86, and this will give you 1. Amplitude of the triangular carrier signals will be 1, and the frequency 7 times faster, isn't it? So therefore frequency is 350 volts. 7 times 50 will give you 350 hertz. Okay, so you compare that. Now let's look at the waveforms. Right, so let's look at this sinusoidal PWM1, the sinusoidal DRY. Let's look at the waveform first. Okay, there you are. So this is modulating signal, the triangular carrier signals, and we already know, if I can make it 1 cycles, then we already know this is 21 degree, right? This is 21 degree, this is 61 degree approximately, this is 66. Okay, and then this is pretty much the other angles there. Okay, so now let's look at the output voltage. This is only the control signals to the switch. Then let's look at the output voltage measure. Add screen. So we look at the output voltage. We look. So there is the output voltage. Okay, so and when you hit this button, fast Fourier transform, it converts, it does the Fourier analysis, and it will convert this time domain into frequency domain, and therefore we're going to look at the harmonic spectrum of both waveforms here. So just ignore that, the first waveform here, just ignore this and look into the V load. So if I can zoom that, if I can zoom, all right, so this is the fundamental component, which is at 50 hertz. Then we see this at actually 350 hertz, the carrier frequency, isn't it? So the characteristics of bipolar PWM, we have fundamental, and we have a component at the switching frequency and its odd multiple. Okay, so our switching frequency is 350 hertz now. So you have a component there and the sideband. Okay, the question asks you what will be the the amplitude of let's look at the equation. Calculate the fundamental component. So we're going to find what if these value. And if you refer to back to the note, okay, this amplitude actually can be calculated by using this equation. Whatever the moderation index is, we have 0.86, isn't it? Okay, and then just simply multiply by 400 volts because this is a full bridge. Therefore, by using that, so we have this equation goes to 0.86 multiplied by 400, and that will give you the the fundamental component. Okay, but the question asks you to um, actually to solve it by using the Fourier series. Okay, by using the Fourier series, then you can get with the fundamental components. Okay, so let's continue. Let's go back to the simulation. Convert that into time domain again. All right. So again, when we talk about the waveforms, it's a AC waveform. We know that the any waveform can be represented by, or is actually a combination of a sinusoidal signals at different frequency with different amplitude. So that also includes this PWM waveforms, and we just observe it the harmonic spectrum by using the FFT grid. So now we're going to analyze, we're going to generate the equation by using the Fourier series to obtain the fundamental component to prove that it is MA multiplied by 400 volts. So 0.86 multiplied by 400 volt. Okay, so let's start. To do the Fourier analysis, what we do is first you need to look into first we just write the general equation. Let me go back to the Jamboard. So let's try look at this, set the background, change to that. Okay, so now we're going to uh, write the Fourier series. Going to do the Fourier series for the output voltage V out bipolar PWM. So we consider a bipolar PWM now. Okay, so before we go further, just write the general equation. So we know that the Fourier series actually can be described by this equation: a naught over 2 f of t a naught over 2 equals to plus the summation, which is n equals to 1 to infinity. Then you have this an cos n omega t plus bn sine n omega t, and that can be changed to transfer to a naught. This is the ultimate objective, is to get that in terms of cn. So we have n equals to 1 to infinity, and then you have cn sine n omega t plus vn, and we know the cn was equals to an squared plus bn squared, and we can also find the angle vn, which is always angles inverse tangent, not inverse tangent, an over bn. So what is a an? An equals to 2 over t integration 0 to t, the equation, the waveform, so the equation f of t multiplied by cos n omega t dt. Then for bn, you know that it's a 2 over t 0 to t again, f of t, now it is sine n omega t dt. So the first step, always write the general equation. Then we move into looking into the symmetry of the waveform. Right. So we look into the symmetry of the waveform, whether the waveform has even symmetry, or it is odd symmetry. Is it half wave symmetry? Okay. and therefore if the waveform is odd in half wave, so it become odd in quarter wave. Great. So it gonna be so three symmetry there too. So let's look at the waveform again. This is one cycle and this is another cycle. So let's assume how to determine whether it's an even waveform. So you just simply reflect with respect to y-axis, and the waveform must equals to the original waveform. The reflection should be equals to the original waveform, isn't it? So let's try to I'm going to divide that or rearrange, reposition, so that the waveform start from here. It is 0, right? So you have positive and negative waveforms there. Okay, so first to check whether it's even, you need to reflect respect to y-axis, and if the waveform is similar to the original waveform, then it is even symmetry. So let's have a check. So this is your, I think I need to remove the top screen here, delete that screen, so only left this. Okay, so okay, right, so this is y-axis and x-axis again. So y-axis, x-axis. Okay, right, so just reflect to check whether it's even symmetry. Reflect with respect to y-axis. Do you get the same waveform? No, isn't it? So that it is not the even symmetry. Okay, so let's check for odd. So how to do the odd? You reflect respect to y-axis, and then you reflect respect to x-axis. You have to do step. First, reflect respect to y-axis, and then you reflect respect to x-axis. If the final waveform similar to or equals same original waveform, then it is odd. So in this case, if we reflect full the waveform, so you will get that. Very okay. Just give a go. Okay, so you get that, and then you reflect respect to y-axis. So if you reflect back, now the waveform is similar to the original waveform. So that means this PWM waveform actually is the odd symmetry. Okay, odd symmetry. Okay, so that's fine. This is odd symmetry. Next, to check whether this is half wave symmetry. So this is one signal, isn't it? One cycle. Okay, so the procedure is, the step is shift to the left half cycle. So you need to shift this to the left half cycle. Okay, okay, so that move to, if you do, so you move to that, great. So that we move to here. I hope you can imagine, right? You can look back, shift to the left half cycle, and then you reflect respect to x-axis again, and you will get the same waveform. Okay, and so therefore this PWM bipolar equals to odd and half wave, and therefore the waveform is odd and quarter wave. Quarter wave, odd and quarter wave waveform. Okay, so let's write it. I'm going to write that the bipolar PWM with, I need to jot this down, with the frequency ratio of 7, which is odd. We're going to find that the output voltage V out is odd and half wave symmetry, and therefore this is also odd and quarter wave symmetry. Okay, So once we know that, then we look into the characteristic of this odd and half quarter wave symmetry. So if you refer back to the previous note on the Fourier series, if the waveform is odd and quarter wave, okay, so you only integrate up to t over 4, the quarter of the wave, yeah, t over 4, which is equals to 90 degree, is it, or pi over 2, right? You just integrate, evaluate up to t over 4, the quarter of the period, so 90 degree. And what else? The characteristic is an always equals to 0. So all value of an will be equals to 0. And bn equals to 2 over, now it will change. If you look at it, the general equation, it is bn equals 2 over t, isn't it? So this is general equation, but since this is quarter wave, then it becomes bn t over 4. Okay, and then you integrate 0 to t over 4 again, the equation, then you have sine n omega t dt, sine omega t dt, and this is only for odd n. This is only true for odd n. If the n is even, bn equals to 0 again. Okay, so you don't have to worry on even n harmonics. You only look into the odd harmonics, 1, 3, 5, 7. Okay, so now we rewrite the bn. So we have 8 over t, 0 to t over 4. Then we have f of t sine n omega t again dt. Now convert that into radian, then we get 8 over 2 pi. This is 0 to 2 pi, so we have pi over 2 now. F theta sine n theta d theta. Just do that, okay? And so we simply that now we have 4 over pi. We just integrate from 0 to pi over 2. F theta sine n theta d theta. Okay, so this is what you need to evaluate. And let's look at the waveform again. Okay, I think I need to get another screen. Add screen the sinusoidal. Okay, right, so this waveform. So so let's convert that into one cycle only. Leave only one cycle. There you are. Great. Okay, so this is 90 degree. So we're going to evaluate up to 90 degree, which is equal to pi over 2 here. So you're going to have 1 integral, 2 integral, 3 integral, 4 integral. Great. So there will be 4 integral. 4 integral. And we already know that this is 0 degree, 21 degree, 61 degree, 60 degree, and this is 90 degree. Okay, so we start with these two, the first integral here, which is from 0 to 21 degree, and the value is minus 400. Yeah, the amplitude is 400. So go back to here. Right. So we have Bn equals to 4 over pi. So the first integral will be 0 to theta 1, which is theta n1. 0 to theta n1. And then f theta is minus 400. And then you have sine n theta d theta. Then you have plus The next integral actually from theta n1 to theta p2. This is 400 multiplied by sine n theta d theta. Next will be from theta p2 to theta n2, and it will be minus 400 sine n theta again d theta, and finally the integral from theta n2 to pi over 2, and this is 400 sine n theta d theta. Okay, right? So you have that, and I hope I can wait there. Let's continue. So let's change everything to radian. I'm going to refer to this, and if you look at the solution, there is one component. If you look at this solution here, there's a missing. It should be 4 integrals. There is another one which is plus omega. From here I write the omega t3 to be consistent with the solution. So this should be omega t3 up to pi over 2, and this is e sine and x dx, right? And then close. Okay, please take note, right? There is a missing, you can delete that as well. So there's another missing integral in this solution. Okay, should be omega t3 to up to pi over 2 e sine x dx, right? Okay, so go back to I just want to get the angles in radian. So we have 1.067. So this is the first, wait, where is it? Okay, this first. So that will be theta p1. Theta p1 equals to 0, and then this is theta theta n1 equals to 0.378. So I'm going to go back to here. So I'm going to change to here. So this is 0. This is that 0.378. So this should be 0.378. And then next 1.067. So this is 0.378, 1.067, and this from 1.067 to 1.169, 1.169, and the final integral will be from 1.169 up to pi over 2. Okay, so that's pi over 2. So I think I can leave you here. You just simply integrate, and then you substitute all the equations here and try to get what is bn1, right? bn1. So you replace everything with bn1 because we want to look into the fundamental. So fundamental n should be equals to 1, not bn1. It's a b1. Okay, so you need to look at to b1. So what will be the answer for b1, and therefore from there you will get c1 equals to a is 0 already, so you have b1 squared, and you get whatever the value of b1. So c1, the amplitude of the fundamental components, equals to b1. So and this must equals to, so you do the integral, that should be equals to MA multiplied by E. The input voltage, which is 0.86, should be equals to multiplied by 400 volt. Okay, try that, right? Then you get the fundamental components. Okay, so what about if the question asks you what will be the carrier? Okay, the carrier. What is the carrier component? Question asks you to get what is the carrier component, which is that value. Is it? This is 350 degree, 350 hertz, which is equals to the FC. Okay, what would be that component? So how to do that? This only happens at n equals to 7, isn't it? 350, so n equals to 7. So you need to replace here, replace everything with n equals to 7. Okay, so you have 4 over pi minus 400 sine 7 theta d theta, and then 400 sine 7 theta. So replace n with the number 7, and n equals to 7 to get the carrier component. Okay, carrier component. So the question could ask you is to find what is a carrier component. Okay, so I'm going to share with you the solution here, but be careful. There is a missing integral, right? Take note of that. There's a missing integral. Or probably I can write that straight away. If I can use this. I can write. Okay, I can write here. So the missing plus, I'm going to put plus. I'm going to remove this bracket. Plus, there's another integral, which is where there is a bracket here. There's too many brackets actually. So just remove these two brackets. Okay, and plus the other integral is actually from omega t3 to pi over 2 e positive e sine nx dx, and then close bracket. Okay, just write that bracket. So I think this is not right. Okay, just right, and this is should be b1 as well. B1, not A1, but B1, rather B1. Okay, so try to do that. I'm going to share with you, and then I'm going to share with you the simulation as well, simulation file. So try it out and look into the and try to do also the example, the exercise. In this page there is a 2 problem. Try to do it, try to simulate, and try to look at the answers of this. Okay, right? So I hope you give a go, give a try. Take this seriously. Okay, take this. Look. We expect you to know how to derive. Okay, is it unipolar, bipolar? You'll be able to explain everything. And actually I take there is a note here. Equation of the triangular waveform will be different. Okay, if you have an M-shaped triangle, it's used, and now it will start with first positive slope, so you get different equation. Okay, and further, right, that's it. Okay, and that's it. Thank you.